In the last batch of videos, we looked at Markov chains, which were tools for describing processes that are probabilistic in nature. And what we saw is that we could treat them like a difference equation or a discrete dynamical system where we still had a state variable that was updated using a simple equation. In this case, we said that the new state was equal to a matrix times the old state. But the difference from this sort of discrete dynamical system and the ones that we'd studied previously was that in this case, the state variable represented the probabilities of lying in one of a finite number of different states. And we looked at some examples. We saw that you could use this to describe the rental car model and talk about the probability that a vehicle would be in Orlando or Tampa on a given day. We also looked at a simple weather model. We could look at the probability that it would be sunny or rainy on a given day. Again, all of this was trying to describe how those probabilities would evolve over time. And the fundamental principle that governed all Markov chains is that these are processes that don't have memories, and so the probability for tomorrow depends only on what the state is today. All right, now these ideas can be extended to a wide variety of different systems. You could use them to describe many different games like Monopoly or Chutes and Ladders, where the next state just depends on where you are now. If they involve dice, then there's no memory effect. On the other hand, games that have cards do have a memory because as you play cards, it changes the cards that are remaining in the deck, and so that can adjust future probabilities. Some other processes that you can describe with Markov models include random walks, which we'll look at quite a bit later on. Baseball is another fun example. You can think of baseball as having a finite number of states if you take into account the number of strikes, balls, outs, and the inning number, as well as people on base. And you can talk about probabilities of transitioning from different states based on who's at bat. Also, there are many biological examples, such as inheritance of traits from a previous generation. So lots of applications of Markov models. Now, what I want to do in the next batch of videos is take a look at a different approach for describing probabilistic processes. So before we do that, let me remind you of our rental car model and what the solutions look like. We had this model. I'll bring it over to the screen here, where we we said, suppose a car starts in Orlando. We'd like to know what's the probability that it ends up in Tampa on a given day. And initially, we had a probability of 1 that it was in Orlando and a probability of 0 that it was in Tampa. And by multiplying by this transition matrix, which contained the transition probabilities between states, we were able to see that the probabilities seem to approach some steady state value. And so in the long run, we found that there was basically a 42-ish% chance, which ended up being 3/7 chance that you're in Orlando on a given day, and 4/7 chance that you're in Tampa. Okay, so in this case, the model was completely deterministic, and we could describe probabilities. But we could also think about that process of a car going between Orlando and Tampa as a random process. And we could do that by imagining by flipping a coin for each day, not a regular coin, but rather a weighted coin to determine where the car should go next. So in our original model, we said if you start in Orlando, there's a 60% chance that you stay and a 40% chance that you leave. And so you could imagine, given the car starting in Orlando, we flip a coin. And if it comes up heads, you stay in Orlando. Comes up tails, you go into Tampa. And then once you're in Tampa the next day, you could again flip the coin and then determine whether you stay or leave, and repeating that process over and over again. And you can do that with a computer by generating random variables. We'll talk about the specifics of that later on, but you can use a command called ran to generate a random number. And then using conditional statements like if and else to make decisions based on the outcome of that random process. And if you do that, you might notice that you could get, a single simulation would look something like this. So in this case, I'm using 1 and 2 to represent locations Orlando and Tampa. So the car starts in Orlando, and we flip our weighted coin. And in this case, it looks like it came up heads, so he stays and stays for the first 2 days, and then on the third day goes to Tampa, stays, then goes back to Orlando, then goes back to Tampa, then back to Orlando, and so on. So in this case, rather than getting probabilities as the output of our model, we actually have one possible trajectory of the system. And one trajectory is interesting to look at, but what's often more interesting is what happens if you repeat this experiment many, many times. And so let's say that you were to do this maybe 100 times. What you could then look at is, given that he started in Orlando, what percentage of the time did he end up in Tampa and Orlando on day 1, day 2, day 3, and so on. And so let's look at a couple of snapshots. All right, so if you look at, let's fix that really quickly. That's actually not day 2. That is day 1, since day 0 was the initial one. All right, so there's our new trajectory. And if we do many experiments, we'll see that on day 1, he ended up in Orlando, looks like around 60% of the time, and around Tampa 40% of the time. And notice, if we go back to our deterministic model, that coincides with exactly what the Markov chain told us should happen, 60% of the time and 40% of the time. But here, we're getting at that answer a completely different way. We're running the simulation over and over again, and we're just counting up how many times did it end up in Orlando. Well, it ended up in Orlando on day 1, 60% of our experiments, and similarly 40% of our experiments he ended up in Tampa. And if you look at future days, let's see, so here's after 5 days, you notice that things have switched, so it's somewhere between 43, 44 maybe, and 56, 57, which coincides with about what we're seeing in our Markov chain as well. And then by the time you get out to day 10, you see that it seems like the system has settled down for the most part. It's much more likely to be in Tampa than in Orlando. Now, the difference with this approach of generating a simulation with a random process is that the results will vary each time you do it. So the first time I run the simulation, I'll get a different answer than the second time. But if you do this enough times, then you will see that the probability that you get anything far away from the true frequencies of these events, the true probabilities, becomes very small. So ultimately what you'll see is that if you count up the frequencies of the events and turn them into proportions, that those will approach the true probability as the number of experiments goes off to infinity. So this is what we would call a Monte Carlo simulation, and we'll get into more of the specifics of how you can actually do that in the next few videos.